So up till now, everything that we've looked at in electrostatics has had a kind of an analogous extension in gravity. This lesson is where all of that gets completely tossed out the window. We're going to look at the concept called voltage. So this first example is just a bit of a review, which we're going to use to extend into a couple other concepts, or the concept of voltage. So we're going to find the electric field and direction 75 centimeters east of a 2 microcoulomb charge. And that's an easy calculation to do. Electric field from a charge is given by E equals KQ over R squared. 9 times 10 to the 9. Q is 2 times 10 to the negative 6. R is 0.75. We're going to square that, and we're going to find that the electric field at that point is 32,000 newtons per coulomb. So what that gives us is a neat way to, or it's a simple way to find the force on a couple different charges if we place them at that point. So for B, C, and D, we want to find what it would be like for a 1 coulomb charge, a 1 millicoulomb charge, or a 2 millicoulomb charge, what the force would be for each of those. So the force on a charge Q in an electric field E is given by that formula there. And so we've got 1 times 32,000 is 32,000 newtons. Similarly, we can just use F equals QE for the other two as well. 1 millicoulomb is 0.001 times 32,000 equals 32 newtons. And 0.002 times 32,000 is 64 newtons. So we can use, we can use the electric field to tell us what the force is going to be of a charge at any given point. The electric field, if we take, kind of look at both of these things, the electric field tells us the newtons per coulomb of force, or the newtons of force per coulomb of charge that will exist at a certain point. Now, there is an analogous concept, except it involves the potential energy. So the potential energy formula that we had yesterday was PE equals KQQ over R. So the potential energy tells us how much potential energy exists between two charged objects. The concept of voltage actually plays an analogous role to the electric field and force, except it plays it with potential energy here. It tells us how many joules of energy an object would have if it were placed at a point. So it similarly to, I'll write these out here. F equals F equals KQQ over R squared. Just like this piece here gave us the electric field, it's this piece here that is going to give us the KQ over R, is going to give us this idea of this concept of voltage. The potential energy is effectively what voltage is. So there's two expressions we can use for it. Voltage is either the potential energy per charge, as the definition I gave you here, joules of energy per coulomb of charge placed at that point. So PE over Q. We can also see, though, that voltage is can be given by another formula here. So PE equals QQ over R over Q. These two Q's are going to cancel, and we're going to get an expression for voltage. That's KQ over R. And just like we had with potential energy, we want to include the positive and negative on the charge. So this is fundamentally different than anything we looked at in gravitation. With gravity, we looked at, okay, what's the potential energy? And that was sufficient at a given point for a setup of objects. But now in electrostatics, this idea of voltage ends up being quite useful. This idea of a potential energy. What would the potential energy be if I placed an object at this point? And so that's where this concept of voltage comes in. It's notoriously confusing, but that's okay. We're going to use it. We'll jump ahead to example 3. This is one of those things that the concept here of voltage is one of those things that it's almost easier to just accept and then learn how to use as you go. At least that's what I found. So we want to find the potential, or also called voltage, 75 centimeters east of this charge. So the voltage at that point is going to be kq over r, or the potential energy, also just called the potential. So 9 times 10 to the 9. Q is 2 times 10 to the negative 6. R is 0.75. So the voltage there is 24,000 joules per coulomb of charge. So then if I wanted to find out what the potential was for B, C, and D, the potential, if we flip back and take a look, the potential is just going to be Q times V. And that came from this expression right here. So PE equals QV is going to give us 24,000 times 1 coulomb is just going to be 24,000 joules. So if I placed a 1 coulomb charge right there, it would have a potential energy of 24,000 joules. We can do the same thing for C and D. 1 millicoulomb is going to be 24 joules of potential energy, and then 2 millicoulombs is going to be 48 joules of potential energy. And if you want to run those calculations, you'd be welcome to do that yourself. So if we know the change in voltage, or the potential difference between 2 points, we can actually use this to find the work required to move a charge between these 2 points. And this is where this concept starts to become really quite useful. So we want to find the voltage at point X and the voltage at point Y. So I'm going to do this in 2 different colors. I'll do this guy in pink. I don't know if you can see that. Whatever. So I'll find the potential for this guy at X. It's going to be given by V equals KQ over R. So we have 9 times 10 to the 9. Q is 2.5 times 10 to the negative 6, and it's positive. And then the distance from here to X is 0.2, which is going to give us a potential at that point of 12,500. We can see that this guy over here is exactly the same. That's part A. We can see that the distance is the same, the charge is the same. So the voltage here from this guy is going to be 112,500. So voltage sums just like energy would. So voltage total is going to equal 112,500 plus 112,500 equals 225,000 joules per coulomb of charge at point X. We can do the same thing here for point Y. V equals KQ over R. K is 9 times 10 to the 9. Q is 2.5 times 10 to the negative 6. R is 0.35. So V at point Y down here is 64,285.7. Nothing's changed over here, same charge, same distance as before. So my voltage down here from this guy is going to be 64,285.7. Really should be putting units on all these things. Joules per coulomb, joules per coulomb. Joules per coulomb, joules per coulomb. And so then the total voltage down here at Y is 128,571.4 joules per coulomb. So we can see the two different electric potentials or voltages at X and Y. So if we go ahead and look at, I'm going to skip C, I'm going to jump straight to D, and you're going to see an interesting relationship here. So energy, we want to find the work required to move a charge. If we were to place a charge here, how much work would be required to move it up here to X? So we found these results. We're not really sure why we've done that yet, but I will show you a really quite neat result that's going to jump out here. So the energy initial is going to be the potential energy at Y plus the work we're trying to find is going to equal the potential energy at X. So I'm going to subtract that over. So work is going to equal the potential energy at X minus the potential energy at Y. Well, the potential energy, we could do it a couple different ways. We could use the potential energy from this guy and our 1.25 millicoulomb charge and do the same thing here and do all that. Or we could use this new calculation that we've got here where PE equals Q times V. So my work now is going to equal the potential energy at X is going to be Q times the voltage at X minus Q times the voltage at Y. So the work now is going to be Q. I can factor out the Q's, and this is going to be Q times the voltage difference between X and Y. And so now I can plug in my values. 1.25 times 10 to the negative 3. 225,000 joules per coulomb minus 128,571.4 joules per coulomb. Do this calculation and we're going to see it's going to take 120.5 joules of work. We're going to have to put energy into the system to make that happen. So this concept of voltage actually ends up being really quite powerful. So I'm going to sum up kind of everything that we've got at this point. This lesson is really quite short. With everything that we've looked at so far. So if the charge begins and ends at rest, then the work will just be the change in potential energy in which is the charge times the change in voltage, which is a cool result. It would have been better if that had been on the previous page, but that's okay. We're going to use this blank page to write up a summary. Just to nail down everything that we've looked at and all the different concepts. So I'm going to draw. Here we go. So here we go. First one, we're going to have electric force. And then we're going to have electric field. And then down here, we're going to have electric potential energy. And voltage, also called electric potential. Sometimes just called potential, as if it weren't confusing enough already. So for electric force, what we want to remember is this. The formula here, F equals KQQ over R squared, and we do not use positive or negative on Q. We use the charges to give direction. So for example, if I had a positive charge there, a negative charge there, and a positive charge there, there would be a repulsive force this way, there'd be an attractive force this way, and then we'd have to add vectors. The way we add vectors, either components or tip to tail, you can choose. Electric field is similar. E equals KQ over R squared. Again, no positive or negative used here. We use charge to give direction. So if I had a positive charge here and a negative charge here, and I just wanted to know what the electric field was at some point in space, the electric field from the positive would be going that way. Electric field from the negative would be going that way. And we would just add the vectors. So that's electric field and electric force. Electric potential and voltage have a similar relationship to each other. We here for electric potential energy, PE equals KQQ over R. It also equals Q times V. For energy, we do use the positive and negatives. Energy is not a vector. And the PE total is equal to just the sum of the potential energies, PE plus PE plus PE. And I'll draw a picture in here. Let's say I had this setup. I call that guy 1, 2, and 3. Then to find the total potential energy of this system, we would just take the potential energy between 1 and 2, the potential energy between 1 and 3, the potential energy between 2 and 3, and we just add them all up algebraically. They're not vectors. Energy is not a vector. We can just add it. Voltage is similar. V equals KQ over R. It's also equal to the potential energy divided by Q. Again, we use positives and negatives. Voltage is not a vector. And just like with potential energy, V total equals the sum of all the voltages from all the different sources in a particular problem. So this is a summary of all the previous lessons. So what I want you to do is I want you to do what you can to make sense of this stuff using some practice exercises. I want you to look at the following questions. I want you to do 1, 2, 4, 5, 9, and 13. As always, if you have any comments, questions, concerns, feel free to let me know.